There's a comet passing Earth tonight that doesn't behave like a comet. 3i Atlas maintains perfect sunlock orientation while bending around gravitational fields in ways that suggest navigation, not drift. The chemistry's wrong. The trajectory's too clean. The timing's too convenient. Avi Loeb's analysis reveals geometric relationships that natural objects don't produce, and suddenly we're faced with an uncomfortable possibility. What if this isn't a rock? What if it's reconnaissance? A technological scan of our system? We're going to walk through the Trojan horse hypothesis, the industrial chemistry anomalies, and the beam that shouldn't exist. By the end, you'll see why this might be the moment everything changed, and we're only just beginning to notice. If these anomalies have you questioning what we're actually witnessing tonight, like and subscribe to Follow the Analysis as 3i Atlas makes its closest approach tonight and continues toward Jupiter. Comment below with where you are, what time the closest approach happens in your time zone, and your honest assessment. Natural object behaving strangely, or something else entirely. Part 1. Tonight is the event. You're reading this at a very specific moment in time, not because you stumbled upon it by chance, but because tonight, right now, something is happening above your head that might never happen again in human history. An object we're calling 3i Atlas is making its closest approach to Earth, and if Avi Loeb is even partially correct, we're not watching a flyby. We're participating in a test. Let me be clear about what closest approach usually means in astronomy. Most of the time, when scientists talk about objects passing near Earth, they're describing a mathematical moment, a point on a graph where two trajectories intersect at their minimum separation. It's a geometry problem, clinical and predictable. We calculate it, we observe it, we move on. The object was never visiting us any more than two strangers passing on opposite sides of a highway are visiting each other. It's just math in motion, and the universe is full of it. But 3i Atlas isn't being framed that way anymore. Something shifted in the language around this object over the past few weeks. Scientists who initially called it unusual started using words like coherent and systematic. Loeb, who's made a career of saying the quiet parts out loud, published an analysis that reads less like a research paper and more like someone trying very carefully to tell you that your house might be on fire. He's not yelling. He's just pointing at the smoke and asking if you smell it too. Here's what makes tonight different. This isn't about distance. It's about timing, geometry, and something far more unsettling. The possibility that we're watching a Black Swan event as it actually happens. You know what a Black Swan is, right? Nassim Taleb defined it as an event that's rare, has extreme impact, and is only obvious in hindsight. The important part is that third characteristic. Black swans don't announce themselves. They look like noise until suddenly they're the only signal that ever mattered. September 11th was a black swan. The 2008 financial crisis was a black swan. They're the moments where everyone afterwards says, how did we not see this coming? Even though all the pieces were visible the entire time. Loeb's argument is that 3i Atlas might be the first black swan we can actually see forming. Not after it happens, not when historians piece it together. Right now, tonight. And that should make you deeply uncomfortable, because it means we're in the before time of a potential paradigm shift, and before times are always filled with people confidently explaining why the thing that's about to happen can't possibly happen. Let me address the fear part first, because I know that's sitting in your mind. There is no confirmed threat here. No one is predicting an impact, an attack, or any kind of disaster scenario. That's not what this is about. This is about significance, not danger. Those are very different things. You can have a historically transformative event that doesn't involve anything dramatic happening at all. Sometimes the most important moments are the ones where we simply realize something we didn't know before. Columbus landing in the Americas didn't require explosions. It just required recognition. What changed in the scientific conversation around 3i Atlas is the pattern recognition. Early observations noted anomalies, odd behaviours that didn't quite fit. Then more data came in, and those anomalies started correlating with each other. Then the correlation started suggesting a system, a logic, an underlying architecture that natural explanations struggle to account for. Loeb's rhetorical progression mirrors this. He started with, here's something strange. Then he moved to, here are multiple strange things that might be connected. Now he's at, here's what it looks like when you treat them as a unified phenomenon. That shift is everything. It's the difference between This rock is oddly shaped, and this rock is shaped like a key, and we're standing in front of a door. Neither statement proves anything, but they orient your attention in very different directions. There's another element to tonight that nobody wants to say out loud, but I'm going to say it. If this object is technological, if it's been under any form of guidance, then it knows we're here. It's been on a trajectory that brings it through our neighbourhood at a moment when we have telescopes pointed at it. That's not a threat. That's observation. And if we're observing it while it's observing us, then what's happening tonight isn't a flyby. It's a mutual assessment. Two intelligences sizing each other up from a distance, neither making sudden moves, both trying to understand what they're looking at. You don't have to believe that for this to be important. You just have to acknowledge that the possibility exists and that dismissing it too quickly might be a mistake we can't undo. Here's the thing that makes Black Swan so psychologically difficult. Nothing dramatic has to happen for this to be historic. If 3i Atlas passes by, continues on its way, and we're left with a data set that doesn't resolve into comfortable natural explanations, that might be enough. The event isn't the passage itself. The event is the moment we stop being able to comfortably categorise what we're looking at. That moment might have already happened, and we're just waiting for the consensus to catch up. Loeb knows this. His writing lately has this preemptive quality to it, like he's trying to get ideas on the record before post-flyby narratives have a chance to sanitise them. Once the object is past us, once the immediate observation window closes, there will be enormous pressure to file this under interesting anomaly, probably natural further study needed. The comfort of that phrasing will be irresistible. But right now, before that window closes, while the data is still coming, in and the geometry is still active, we have a chance to ask the uncomfortable questions without the benefit of hindsight. So what if the real signal isn't the motion at all? What if it's the geometry? What if the way this object moved through space matters more than where it's going? That's the question that leads us into the next layer of this, and it's where the numbers start to tell a story that intuition alone can't explain. Part 2. The 16-degree problem. Gravity bends everything. That's not metaphor, that's physics. When an object falls toward the sun, its trajectory curves, accelerates, and then curves again as it swings back out into space. This is called perihelion gravitational deflection, and it happens to every comet, every asteroid, every piece of space debris that comes close to a massive body. The amount of deflection depends on velocity, mass, and how close the object gets. It's predictable. We've been calculating these trajectories for centuries. 3i Atlas underwent a reported 16.4 degree trajectory bend at perihelion. Let me be very clear. This is reported analysis, not universal consensus. Different observation teams, different modelling approaches, different margin of error calculations. But multiple independent analyses keep arriving at numbers in this range, and that consistency is what makes people nervous. 16.4 degrees is not by itself anomalous. Objects deflect. That's normal. What's not normal is what that number relates to. 3i Atlas has been exhibiting what astronomers call non-gravitational acceleration. It's speeding up in ways that gravity alone doesn't explain, and that acceleration appears to be coming from a jet of material pointing sunward. Not away from the sun, which is what comets usually do when solar heating causes outgassing. Toward the sun. The jet has an opening angle of approximately 8 degrees. Now, let me walk you through why that matters. 16.4 divided by 2 is 8.2. The gravitational deflection is almost exactly twice the jet opening angle. That's not close. That's eerily precise. And precision, in a system that should be chaotic, is the sound of alarm bells that scientists try very hard not to ring too loudly. Here's the metaphor that makes this click. Imagine you're throwing a ball, and as it arcs through the air, it releases a thin stream of water. Normally that water spray goes everywhere, tumbles, disperses, follows the chaos of fluid dynamics. But what if the stream stayed perfectly aligned with the ball's trajectory? And what if the angle of the spray adjusted in real time to match the curve of the throw? You'd stop thinking about water pressure and start thinking about intent. That's what this 2-to-1 ratio suggests. It suggests that as 3i Atlas bent around the sun under gravitational influence, its jet orientation adjusted to maintain a specific geometric relationship. The term being used very carefully in some of the technical discussions is perfect handoff. Gravity changes the object's path. The The jet compensates. The orientation stays locked. Random outgassing does not do this. Comets tumble. They spin. Their jets wobble and precess and shut off and reignite based on which patches of ice get hit by sunlight. The geometry is chaotic by nature. Maintaining a symmetric relationship through perihelion, where gravitational forces are strongest and rotational dynamics are most unstable, is like keeping a spinning top perfectly upright while someone shakes the table underneath it. Let me explain why symmetry through perihelion is such a big deal. As an object approaches the sun, it's being pulled forward and inward. Gravitational torque doesn't just change velocity, it changes angular momentum, orientation, spin state. For a natural body, especially one that's already tumbling and outgassing, perihelion is a blender. Everything gets scrambled. Maybe you come out the other side with a new rotation rate and new axis, jets pointing in completely different directions. That's normal, but if you come out the other side with your orientation preserved, with your jet still pointing in a direction that makes geometric sense relative to your new trajectory, that means something resisted the scrambling. Something maintained attitude control through the chaos. Gravity is supposed to be the explanation for weird trajectories. It's the universal get-out-of-jail-free card for anything moving strangely in space. Gravity did it. But when gravity becomes part of the pattern instead of the explanation, when it seems to be incorporated into the behaviour rather than dictating it, that's the moment you stop looking for natural causes and start asking different questions. This is what Loeb means when he talks about the geometry not lying. You can argue about interpretation. You can debate whether jets are artificial or natural. You can question measurement precision. But you can't argue with the 2-to-1 ratio without proposing a mechanism that maintains it. And so far, nobody's proposed one that doesn't involve either extraordinary coincidence or some form of active control. Here's where the discomfort comes in. If the jet opening angle adjusted to match half the deflection angle, that means the adjustment happened in response to the gravitational environment. That's not just thrust. That's navigation. That's using gravity as an instrument, as a tool, as something to work with rather than something to passively experience. And natural objects don't navigate. They drift. They fall. They react. They don't plan. The alternative, of course, is that this is all coincidence, that we're seeing patterns in noise, finding faces in clouds, that the 2-to-1 ratio is an artifact of measurement error or selective attention, or wishful thinking. Maybe. But coincidences have a cost too. Every time you invoke chance, you're spending from a limited budget of credulity. 1 coincidence is free, 2 is plausible. 15 starts to look like a confession. And if maintaining this kind of orientation through perihelion is possible, if it happened once, then it's been happening the entire time, which means we need to talk about what it takes to keep something pointed at the sun for months on end, while gravity tries to spin it like a coin. Part 3. Continuous sun lock. Why orientation is everything. Spacecraft engineers will tell you that pointing is harder than pushing. That's not intuition. That's brutal experience bought with decades of failed missions and billions of dollars in corrective burns. You can strap a rocket to almost anything and make it go faster. Making it face the right direction while it goes faster. That's where the engineering gets expensive. Here's why. In space, there's no friction, no air resistance, nothing to damp out rotation. If something starts spinning, it keeps spinning. If it wobbles, it keeps wobbling. And everything in space is spinning, because everything got here by bumping into other things, and every collision imparts angular momentum. Natural bodies, asteroids, comets, they tumble. They tumble in complex, chaotic ways, sometimes rotating around multiple axes simultaneously. It's called passive tumbling, and it's the default state of small objects in space. Controlled attitude is different. That's when something maintains a specific orientation relative to an external reference, like the sun or Earth or the direction of travel. Satellites do this. Spacecraft do this. They do it with reaction wheels, with thrusters, with careful planning and constant adjustment, and even then they drift. Attitude control is an ongoing battle against the chaos of rotation, and it requires energy, sensors, computation, and something making decisions. 3i Atlas has apparently maintained a sunward-facing orientation for months. Not approximately sunward, not occasionally sunward, consistently, precisely, lock-on-target sunward, while tumbling through space, while undergoing gravitational deflection, while outgassing, while being a comet-like object that should, by all rights be spinning like a drunk penguin. There's a concept in spacecraft design called pole switching. It's a maneuver where you intentionally flip your orientation by 180 degrees, usually to manage thermal loads or reorient solar panels, or point instruments in a new direction. It requires planning. You have to spin down your current rotation, execute the flip using thrusters or momentum wheels, then stabilize in the new orientation. Loeb has speculated, very carefully, that 3i Atlas might have performed something like this, not because we saw the flip itself, but because the before and after orientations suggest it happened. Let me explain angular momentum damping in terms that don't require equations. Imagine you're on a spinning office chair. You're rotating. To stop rotating, you need to push against something, the floor, the desk, anything that can absorb your momentum. In space, there's nothing to push against, so you have to throw something. You eject mass in one direction, and conservation of momentum changes your spin in the other direction. Comets do this accidentally through outgassing. Spacecraft do it deliberately through thrusters. But here's the problem. Random outgassing creates random torque. It speeds you up, slows you down, tilts you in directions you didn't plan for. It's like trying to stop a spinning chair by randomly throwing tennis balls in every direction. You might slow down eventually, but you're not going to end up facing a specific direction. You're definitely not going to stay facing that direction for months afterward. Natural bodies, especially after perihelion, should be rotationally scrambled. Gravitational torque does not preserve orientation. It disrupts it. Think about what happens when you spin a coin on a table and then shake the table. The coin doesn't keep spinning smoothly in the same orientation. It wobbles, precesses, eventually falls over. Perihelion is the shake. The fact that 3i Atlas came out the other side still sunlocked means something resisted the wobble. You can propose a natural mechanism for that resistance, but you have to explain how it works. You have to show how random outgassing, random mass ejection, could consistently produce torque that corrects for gravitational perturbations in real time. That's a control system. That's feedback. That's sensing your orientation, comparing it to a target, and adjusting your behavior to minimize error. And natural objects don't do feedback. Here's another way to think about it. Orientation implies purpose, not just motion. If something's moving fast, maybe it got hit by something. If something's accelerating, maybe it's outgassing. But if something's maintaining a specific orientation over time, despite environmental perturbations, that suggests the orientation matters, that there's a reason for it, that facing the sun, specifically, serves a function that's important enough to expend energy maintaining. Let me address the most common natural explanation, because I know you're thinking it. Maybe the object has an asymmetric shape or mass distribution that naturally stabilizes it in a sun-facing orientation through radiation pressure or thermal effects. Maybe it's like a badminton shuttlecock, where the shape creates aerodynamic stability even without active control. Okay, maybe. But that requires several things to be true simultaneously. The asymmetry has to be significant enough to overcome tumbling from gravitational torque. It has to be aligned in exactly the right way. It has to persist through perihelion without being disrupted. And it has to explain the jet orientation, and the trajectory adjustments, and the timing and everything else. You're not proposing one mechanism anymore. You're proposing a cascade of fortunate circumstances, each one individually unlikely, all of them happening to align in ways that mimic deliberate control. At some point, the natural explanation becomes more complicated than the artificial one, and that's deeply uncomfortable, because we're trained to prefer natural explanations even when they require intellectual gymnastics. Occam's razor tells us to prefer simpler explanations, but somewhere along the way we started confusing simple with familiar. So if orientation control is this hard, if it requires this much precision, then why do it? What's the payoff? Why would something go to all this effort to keep facing the sun unless facing the sun was the entire point? Unless the orientation itself was the mission, not just a side effect of some other behavior? That's the question that leads us into territory that makes scientists extremely nervous. Because once you start asking why, you're assuming intent. And intent is the third rail of this entire conversation. Touch it and everything explodes into arguments about burden of proof and extraordinary claims. But we're already here. We might as well ask. What if looking natural is the strategy? Part 4. The Trojan horse isn't a metaphor. Imagine you want to send a probe to another star system. You've got a problem. The destination civilization might have detection capabilities you can't predict. They might see you coming from light years away. They might classify you as a threat. They might intercept you, destroy you, ignore you. You need to get close enough to observe without triggering defensive or dismissive responses. So what do? You dress the probe in something they won't see as artificial. You wrap it in ice and dust. You let it accrete a coating over millions of years of interstellar travel. You make it look from a distance like every other piece of cosmic debris floating through their system. You make them think it's a comet. This is the Trojan horse hypothesis, and I want to be very clear that it's a hypothesis, not a claim. It's a scenario that would explain the observations if those observations are accurate. It's a thought experiment about interstellar reconnaissance strategy. But it's also disturbingly logical once you start thinking through the engineering constraints of long-duration space travel. Here's why a natural exterior makes sense. If you're travelling for millions of years, you're going through interstellar space, which is not empty. It's full of gas, dust, micrometeoroids. Everything out there is getting sandblasted and coated over geological timescales. A probe launched from a distant civilization wouldn't arrive looking shiny and metallic. It would arrive looking like it's been through exactly what it's been through. A million-year journey through the universe's slowest, gentlest version of weathering. That crust explains a lot. It explains why 3i Atlas reflects light like a comet but behaves like something else. It explains compositional anomalies. It explains why spectroscopic analysis shows comet-like surface chemistry, while the underlying behaviour suggests structure. It's not deception. It's just time doing what time does to everything. But there's a detail in the reported analysis that makes this more than speculation. 3i Atlas's water-to-dust ratio, based on spectroscopic measurements, appears to be inconsistent with normal cometary values. Let me be precise. This is reported analysis from specific observation campaigns, not universal consensus. But if the numbers hold, the object is shedding material that doesn't match the expected proportions for ice sublimation. Comets have a pretty standard recipe. They're dirty snowballs, mixtures of ice and rock and organic compounds. When they get near the sun, the ice sublimates, turns directly from solid to gas, and carries dust with it in predictable ratios. You can measure the ratio by analysing the light spectrum of the coma, the cloud of material around the comet, and that ratio tells you about internal composition. If the ratio's off, something else is happening. Either the internal composition is unusual, which would require exotic formation conditions, or the material being shed isn't coming from ice sublimation alone, it's coming from something else. Surface erosion, structural shedding, material being deliberately ejected for propulsion or attitude control. Here's the thing about using mass ejection for propulsion. You don't want to eject clean water vapour. Water vapour is hard to produce if you don't have ice, and if you do have ice, you're limited by solar heating. What you want is dust, particulates, material you can heat and accelerate efficiently using internal power. And if you're wrapped in a crust of accumulated interstellar material, you've got a ready-made propellant supply. You just heat and eject it, and from a distance it looks like normal cometary outgassing, except the ratios are wrong. This is where the dirty appearance becomes strategically useful. If observers see a comet behaving unusually, the first instinct is to classify it as an unusual comet, not a technological object. The natural coating provides cover. It biases classification toward familiar categories, and that bias is powerful. It takes extraordinary evidence to move something from weird natural object to potential artifact, and every layer of natural appearance raises that threshold. Camouflage is a universal strategy in nature. Prey species do it to avoid predators. Predators do it to ambush prey. Military technology does it to avoid detection. Intelligence agencies do it to blend into populations. There's no reason to think technological intelligence operating on interstellar scales wouldn't use the same principle. If you're sending reconnaissance probes to inhabited systems, you camouflage them as natural objects, because natural objects don't trigger alarms. And if you've been travelling for millions of years, the camouflage applies itself. You just have to design the core probe to survive the accumulation and use it. Now, let me address the skepticism directly, because I can hear it. This is unfalsifiable. You're just adding epicycles. Any observation that doesn't fit gets explained away as part of the disguise. Okay, fair, but that cuts both ways. At what point do we stop adding epicycles to natural explanations? At what point does weird comet with multiple independent anomalies become a less parsimonious explanation than object with a crust? The difference between a conspiracy theory and a reasonable hypothesis is whether it makes testable predictions. The Trojan horse hypothesis predicts that internal structure should differ from external appearance. It predicts compositional gradients. It predicts that if you could sample below the surface, you'd find material that doesn't match. And maybe, given enough data, we'll be able to test that. But right now, with the data we have, we're stuck in the uncomfortable position of having observations that fit the hypothesis without being able to definitively prove it. Which brings us back to probability stacking, because the Trojan horse idea doesn't stand alone. It's part of a larger pattern, a collection of anomalies that either represent the most statistically unlikely comet ever observed, or something else entirely. And patterns matter. One strange thing is noise. 15 strange things that all happen to point in the same direction. That's a message. Part 5. The Black Swan stack. Let me tell you how probability actually works in the real world. If I flip a coin and it comes up heads, that's not surprising. 50-50 chance happens all the time. If I flip it again and it comes up heads again, still not surprising. 75% chance of getting at least one heads in 2 flips. Completely normal. But if I flip that coin 20 times and it comes up heads every single time, you stop thinking about probability and start checking whether the coin is fair. That's probability stacking. Individual events might be explicable. But when you start seeing correlations, when independent variables start lining up in ways that shouldn't happen by chance, the math stops being your friend. 3i Atlas has roughly 15 distinct anomalies depending on how you count them. Trajectory, timing, composition, jet behavior, orientation, non-gravitational acceleration, perihelion alignment, water ratios, spectroscopic inconsistencies, lack of coma development, apparent attitude control, Jupiter trajectory, arrival timing relative to solar cycle, and each one individually can be explained away with enough creativity. But here's what scientists do when they analyze data. They isolate variables. They look at each anomaly separately, propose a natural mechanism, calculate the probability, and if it's within reasonable bounds, they move on. That's good methodology for most situations, but it fails catastrophically when you're dealing with a system, when the anomalies aren't independent, when they're all expressions of the same underlying phenomenon. Think about it this way. If I told you someone won the lottery, you'd think they got lucky. If I told you they won the lottery twice, you'd be suspicious. If I told you they won 15 different lotteries, you'd stop thinking about luck and start thinking about fraud. Same principle here. Each anomaly might have a 1 in 100 chance of occurring naturally. But 15 of them? That's 1 in 100 to the 15th power. That's a number so small it's functionally 0. Navigation systems don't happen by accident. Precise orientation control doesn't happen by accident. Geometric relationships that persist through gravitational perturbations don't happen by accident. Compositional anomalies, timing coincidences, trajectory adjustments that seem to anticipate gravitational fields, these things individually stretch credulity. Together, they break it. And yet, here we are, still having this conversation as if natural explanations are the default position. Why? Because admitting the alternative is psychologically unbearable. Because it means our understanding of what's out there, who might be out there, whether we're alone, all of it gets thrown into question. And humans are really, really good at not noticing things that would force us to update our worldview. There's a term in psychology for this: normalcy bias. It's the tendency to underestimate the probability of disaster, to assume that tomorrow will look like today, that the patterns we've always seen will continue indefinitely. It's why people stay in their homes during hurricanes, why investors ignore warning signs before market crashes, why societies collapse even when the signs of decline are obvious in hindsight. Black swans thrive in normalcy bias. They happen in the gap between what the data is telling you and what you're willing to believe, and the people who see them coming are always dismissed as alarmists, as paranoid, as reading too much into random noise, until suddenly they're not. History is full of cases where patterns were ignored because acknowledging them would have been too disruptive. Continental drift was obvious from the shape of the continents, but geologists rejected it for decades because they couldn't imagine a mechanism. Meteorites were dismissed as folklore because rocks don't fall from the sky. Heliocentrism was resisted not because the math didn't work, but because it displaced humanity from the centre of creation. The pattern here is that paradigm shifts don't happen when the evidence arrives. They happen when the community is ready to accept what the evidence has been saying all along. and we might not be ready. We might need more data, more time, more independent confirmation, or we might be in the last few hours before the shift happens, and everyone reading this in a year will look back and wonder how it wasn't obvious. Black swans are invisible until they're not. That's what makes them black swans. You can't see them while you're in the before time because your entire framework for understanding reality doesn't include the possibility. It's not that the evidence is hidden, it's that the mental categories needed to interpret the evidence don't exist yet. So here's the central question, and it's the only question that matters right now. Are we watching a natural object with a bunch of weird properties? Or are we watching something that was designed to look like a natural object, and the weird properties are the places where the design shows through? I don't know. Loeb doesn't know. Nobody knows. And anyone who claims certainty in either direction is lying to you or to themselves. But the question is on the table now, and it won't go away just because it's uncomfortable. And if there's even a chance, even a small one, that this is real, then the object's trajectory after Earth becomes the most important thing we could possibly be paying attention to. Because maybe Earth was never the destination. Maybe we're just a waypoint. Maybe the real mission is what comes next. Part 6. Jupiter was never just next. Let me tell you something about orbits that most people don't think about. When we describe a trajectory through the solar system, we talk about planets as if they're destinations, stops on a cosmic subway line. Earth, then Mars, then Jupiter, then Saturn. But that's not how orbital mechanics works. Trajectories aren't about where you're going, they're about what you're using. Jupiter is the solar system's gravitational anchor. It's got 318 times Earth's mass, a magnetic field 14 times stronger, and a gravitational influence that extends millions of kilometers into space. When spacecraft designers plot missions to the outer system, Jupiter isn't a destination, it's infrastructure. It's a slingshot, a brake, a pivot point. It's the tool you use to go places you couldn't otherwise reach. 3i Atlas's trajectory takes it past Earth and continues toward Jupiter. On the surface, that sounds normal. Lots of objects pass through the inner solar system and head outward. But the geometry matters. The approach angle, the velocity, the timing relative to Jupiter's position. These aren't random. They're what engineers call a gravity assist setup. You arrive at a specific angle and speed, Jupiter's gravity bends your trajectory, and you leave going somewhere different than you would have otherwise. Now, I need to be careful here. Natural objects can end up on gravity assist trajectories by pure chance. The solar system is full of chaotic orbits, and sometimes things line up. But when you combine a gravity assist setup with all the other anomalies, with the apparent navigation and the orientation control and everything else, it stops looking like chance and starts looking like a flight plan. Here's what makes Jupiter especially interesting. It has what's called a Hill radius, the region of space where its gravity dominates over the Sun's. Inside that radius, objects can settle into stable orbits around Jupiter. Outside it, they fall back to solar orbits. The boundary between those zones is where things get weird. It's where three-body dynamics take over, where you can park objects in semi-stable positions called Lagrange points, where gravitational interactions create pockets of stability in the chaos. Lagrange points are orbital sweet spots. They're places where the gravitational pulls of two massive bodies balance out in ways that let a third, much smaller object stay put without expending fuel. Earth has Lagrange points. The Sun-Earth system has them. And Jupiter has some of the most useful Lagrange points in the solar system because of how massive it is. The James Webb Space Telescope sits at a Lagrange point. The old SOHO Solar Observatory sits at 1. They're perfect for observation platforms, for relay stations, for anything you want to keep in a specific position relative to two moving bodies without constant course corrections. And if you were planning a long-term observation mission in someone else's solar system, you'd absolutely want to position assets at Lagrange points. Now, let me be very clear. There is zero evidence that 3i Atlas is planning to deploy anything at Jupiter's Lagrange points. This is speculation based on trajectory geometry, and what would make sense if this were a reconnaissance mission. But it's informed speculation. It's what human mission designers would do if we were sending probes to another star system. You don't stop, you don't land, you fly through, you scan, and you leave assets in stable positions for long-term observation. Think about how we've used gravity assists. Voyager, Cassini, New Horizons. Every major outer solar system mission has used Jupiter as a gravitational stepping stone. Not because we're obsessed with Jupiter, but because it's useful. It changes your velocity, your direction, your energy budget in ways that would otherwise require massive amounts of fuel. It's free propulsion if you know how to use it. And here's the uncomfortable part. If 3I Atlas approaches Jupiter's hill radius at the right angle and velocity, it could potentially release smaller objects that fall into stable orbits, while the main body continues outward. Those objects would be invisible unless you were specifically looking for them. They'd be small, dark, not emitting anything detectable, just sitting there in gravitationally stable positions, watching. This is where the conspiracy theory alarms start going off, and I get it. I hear how this sounds. But consider the alternative. If this is a technological object, if it came from another civilization, what would their mission profile be? Would they announce themselves? Would they make contact? Or would they do exactly what we do? Observe quietly, gather data, avoid disrupting the local environment until they understand what they're dealing with? Earth might have been secondary. A close pass to get a good look, to measure atmospheric composition, to detect electromagnetic emissions, to catalogue technological signatures. But Jupiter is where you'd set up shop. Jupiter is where you'd leave the instruments that keep watching after you're gone. It's the difference between a flyby and a surveillance network. And before you dismiss this as science fiction, remember that we're already planning to do exactly this. There are serious proposals for interstellar probes that would use similar strategies. Breakthrough Starshot, the interstellar probe concept, all of them involve getting close to target systems, doing rapid surveys, and potentially leaving monitoring equipment behind. It's not crazy. It's just engineering applied to a scale we're not used to thinking about. The timing matters too. 3I Atlas arrived in the inner solar system at a moment when Jupiter is positioned such that a gravity assist is geometrically possible. If it had arrived 6 months earlier or later, the angles wouldn't work. Now, you can argue that's coincidence, that the object's been travelling for millions of years and just happened to arrive at a convenient time. But probability stacking, remember? How many coincidences do we accept before coincidence stops being a satisfying explanation? So if Earth was reconnaissance and Jupiter is infrastructure, what does that make the rest of the mission? Where does 3I Atlas go after Jupiter? And more importantly, if it leaves something behind, how would we even know? We wouldn't. Not unless we went looking. Not unless we specifically tasked telescopes to watch Jupiter's Lagrange points for objects that shouldn't be there. And even then, we might not find anything, because something designed to avoid detection probably wouldn't make itself easy to spot. But the possibility is there now. The idea is on the table. And maybe that's the point. Maybe the real signal isn't the object itself. Maybe it's the questions it forces us to ask about what could be out there that we've never bothered to look for before. Chemistry might have more to tell us than geometry, and chemistry, unlike trajectories, doesn't lie easily. Part 7. Industrial Chemistry in Deep Space. Comets are supposed to be messy. They're not precision-engineered objects. They're leftovers from solar system formation, agglomerated dust and ice that never got swept up into planets. Their chemistry reflects that chaos. They're dirty, inconsistent, full of weird organic molecules and trace elements that vary wildly from one object to the next. That messiness is part of their identity. So when a comet-like object shows clean ratios, consistent composition, chemistry that looks more manufactured than accumulated, people notice. 3I Atlas's spectroscopic analysis has revealed some things that don't fit the standard cometary profile. Again, this is based on reported observations from specific campaigns, not universal agreement. But multiple independent teams have flagged compositional anomalies, and those flags keep pointing in the same direction. Let's start with nickel and iron. These are common elements in space, present in asteroids, in cometary cores, in interstellar dust. But they show up in specific ratios based on formation conditions, temperature, pressure, the chemical environment where the object condensed out of the protoplanetary disk. Natural processes produce a range of ratios, but that range isn't infinite. It's bounded by chemistry, by thermodynamics, by what's physically possible given the conditions. The nickel-to-iron ratio in 3I Atlas, based on some spectroscopic measurements, appears to fall outside the expected range for objects formed in our solar system. Not wildly outside. Not, this violates physics, outside. Just outside. Enough to make you check your calibration. Enough to make you wonder if the object formed somewhere else, under different conditions, or if the ratio is telling you something about processes rather than origins. Here's why that matters. Industrial processes produce consistent ratios. Smelting, refining, metallurgy, any kind of intentional material processing tends towards specific stoichiometric values because you're optimizing for performance. Natural processes produce distributions, ranges, variability. If you find a rock on Earth with an unusual metal ratio, you might conclude it came from an unusual geological setting. But if you find 10 rocks with the exact same unusual ratio, you start thinking about mines and refineries. Then there's cyanide. Hydrogen cyanide is common in comets. It's part of the organic chemistry that happens in cold, dark environments where carbon and nitrogen can bond in ways they can't at higher temperatures. Comets typically have cyanide abundances in a certain range, variable but predictable. Too much, and you need to explain an unusual formation environment. Too little, and you need to explain what destroyed it. 3I Atlas shows cyanide levels that some observers have described as anomalous, higher than typical, but in a specific way that doesn't match the patterns seen in regular comets. And cyanide is interesting because it's not just a fossil chemical. It's also a potential propellant precursor, a building block for certain kinds of energetic reactions. If you were designing a long-duration probe that needed to produce thrust using local materials, hydrogen cyanide could be part of your fuel chemistry. Now, before anyone panics, I'm not saying 3I Atlas is leaking rocket fuel. I'm saying the chemical signature is unusual, and unusual in a way that's consistent with either exotic natural formation conditions or deliberate chemical engineering. Both are possible, neither is confirmed, but the pattern keeps showing up. Let me explain what I mean by clean ratios versus messy natural processes. When you look at a population of comets, their chemistry varies. Comet A has more water, less carbon monoxide. Comet B has more methane, different dust composition. That variability is expected because they formed in slightly different parts of the protoplanetary disk, at different distances, different times, different local conditions. It's like fingerprints. Everyone has different ones. But imagine you found 100 people with identical fingerprints. You'd stop thinking about natural variation and start thinking about cloning, or manufacturing, or some process that deliberately produces consistency. That's what people are noticing in 3I Atlas's chemistry. It's not that any single measurement is impossible. It's that the measurements collectively suggest less variability than you'd expect, more consistency, more precision. Precision in chemistry usually means control. It means processes operating under specific conditions to produce specific outcomes. Blast furnaces produce consistent steel because the temperature, pressure, and timing are controlled. Natural processes operating over millions of years produce distributions because conditions vary. Randomness accumulates. Entropy does what entropy does. If 3I Atlas's composition suggests control, that's another data point in the stack. It's chemistry reinforcing what geometry and dynamics and timing have been hinting at. And chemistry is hard to fake. You can't camouflage stoichiometry. If the ratios are wrong, they're wrong, and no amount of dust coating changes internal composition. There's also the question of what we're not seeing. Comets develop comas, clouds of gas and dust that form when solar heating causes sublimation. The coma is how we study cometary chemistry. We analyse the light from the coma, break it into spectra, identify absorption and emission lines that tell us what elements and molecules are present. It's how we've characterised hundreds of comets over the past century. 3I Atlas has a coma, but it's weaker than expected for an object of its size at its distance from the Sun. That could mean low volatile content, unusual surface properties, or that the outgassing isn't being driven by solar heating alone. If you're using internal energy to eject mass for propulsion, you're not necessarily creating the kind of coma you'd get from pure ice sublimation. You're creating something else, something that looks comet-like but doesn't quite behave the same way. So we've got metal ratios that are unusual, cyanide levels that are unusual, a coma that's weaker than expected, an overall composition that's more consistent than natural variability would predict. Each one explainable. All of them together, that's when you start thinking about industrial chemistry rather than formation chemistry. And if the chemistry is industrial, if there's evidence of processing and precision, then what about the beam itself? What about the jet that's been driving the non-gravitational acceleration and maintaining sunlock orientation? Because jets are supposed to disperse, they're supposed to be messy, and this one isn't. Part 8. The beam that isn't propulsion. Comet jets are chaos made visible. When ice sublimates, it erupts from localized patches, cracks in the surface where volatiles can escape. The gas expands rapidly, carrying dust with it, creating plumes that spread out in cones. Those cones are wide, diffuse, turbulent. They interact with the solar wind, get pushed and shaped by magnetic fields, form the classic comet tail that always points away from the sun. 3I Atlas has a jet, but it's not behaving like the jets we're used to seeing. The jet is narrow, collimated is the technical term. It maintains coherence over distances measured in hundreds of thousands of kilometres, potentially over 1 million. That's not normal. Gas expanding into vacuum should spread out rapidly, following the square of distance. It should disperse, diffuse, lose definition. Think about smoke from a candle. Close to the flame, it's a thin stream. A few centimetres away, it's already spreading out, mixing with the air, losing its shape. Now imagine smoke staying in a tight beam for a kilometre. That's what we're seeing here, scaled up to space. Collimated jets require one of two things, either a very specific nozzle geometry that constrains the flow, or an external force that focuses the material after it's been ejected. Nozzles are engineering. External magnetic fields can collimate plasma, but that requires the material to be ionized and the field to be strong and precisely shaped. Neither explanation is easy to get from natural processes. Let's talk about what it takes to maintain a 1 million-kilometre beam. First, you need sustained mass ejection from a consistent source. That means a reservoir of material that doesn't run out, doesn't vary in output, doesn't shut off when the sun's angle changes. Most comets show variable outgassing. Jets turn on and off as different patches of the surface rotate into sunlight. They flicker, pulse, change intensity. A steady jet requires either a massive reservoir or continuous replenishment. Second, you need to prevent dispersion. Gas molecules in vacuum travel in straight lines once they're free from the object, but they also have random thermal motion. That randomness causes spreading. To keep a beam tight, you either need the molecules moving very fast in the beam direction compared to their thermal motion, which means high ejection velocity, or you need something actively confining them. High ejection velocity from ice sublimation is hard to achieve. You're limited by the energy available from solar heating. You can get maybe a few hundred meters per second under ideal conditions. To maintain collimation over 1 million kilometers, you'd need velocities significantly higher, or some other mechanism keeping the flow organized. This is where the shielding hypothesis comes in, and it's speculative, but it's the kind of speculation that engineers engage in when trying to explain observations. If the jet is protected from solar-wind interaction, if there's some kind of magnetic or electrostatic shielding preventing dispersion, then you could maintain collimation over much greater distances. Spacecraft use magnetic nozzles in some ion drive designs for exactly this reason. You create a magnetic bottle that channels plasma, keeps it focused, extracts momentum more efficiently. Could a natural object do this? Maybe, if it has an intrinsic magnetic field and the right geometry. But most comets don't have significant magnetic fields. They're too small, not differentiated, no dynamo action. So you'd need to propose that 3I Atlas is unusual in yet another way, that it has magnetic properties comets don't typically have, and that those properties just happen to be configured in a way that creates beam collimation. Or you accept that the jet is being actively managed. Here's another angle. The jet points sunward, not away from the sun, which is what you'd expect from solar heating driving outgassing. Toward the sun. That means the thrust from the jet pushes the object away from the sun, which would normally slow it down as it approaches perihelion and speed it up as it leaves. But 3I Atlas's trajectory doesn't show the kind of deceleration you'd expect from sunward thrust. Instead, it shows the coordinated acceleration-deceleration pattern consistent with using the jet for attitude control and trajectory adjustment. That's the difference between propulsion and manoeuvring. Propulsion is about going faster or slower in the direction you're already moving. Manoeuvring is about changing direction, maintaining orientation, fine-tuning your path. And manoeuvring requires a control system, sensors, feedback, decision-making. You can't maneuver by accident. The beam might not be propulsion at all. It might be a reaction control system like the small thrusters on a satellite that keep it pointed the right way. You're not trying to go anywhere faster. You're trying to stay aimed correctly while you coast. And if you're trying to stay aimed at the sun while your trajectory bends around it, you need continuous, precise adjustments. Mass ejection for attitude control is standard spacecraft design, but it's engineering, not geology. Natural objects don't stabilize their orientation by ejecting material in carefully calculated directions. They tumble, they wobble, they do whatever chaos dictates. Stability requires intent. And then there's the question of why. If you're using precious mass to maintain sunlock, that mass better be buying you something important. What's so critical about facing the sun that you'd spend your propellant budget maintaining that orientation for months? What are you doing that requires continuous line of sight to the solar disk, communication, power collection, thermal management, instrument alignment? Those are the reasons spacecraft maintain sun pointing. Those are engineering considerations, not natural behaviours. And if 3i Atlas is maintaining sun pointing for any of those reasons, then we're not talking about a comet anymore. But maybe I'm getting ahead of myself. Maybe all of this, the trajectory, the chemistry, the beam, maybe it's all extraordinary natural phenomena that we just haven't seen before. Maybe 3i Atlas is teaching us that the universe is weirder than we thought, that comets can do things we didn't know comets could do, that our models need updating. That would be the comfortable answer. And maybe it's the right one. But there's another possibility. One that's starting to look less like speculation and more like a framework that actually explains the data. And that possibility is quietly changing the conversation in ways most people haven't noticed yet. Part 9. The Loeb Scale. Quietly changes everything. You probably haven't heard of the Loeb Scale. It's not in textbooks yet. It's not taught in astronomy courses, but it exists. It's being used, and it represents a fundamental shift in how we approach the question of technological artifacts in space. The Loeb scale is a classification system for assessing the likelihood that an observed object or phenomenon is technological rather than natural. It's modelled after other scientific scales like the Torino scale for asteroid impacts, or the Rio scale for SETI detections. It's a way of quantifying uncertainty, of moving from binary yes-no thinking to probabilistic assessment. And 3i Atlas is the first major object to be publicly evaluated using this framework. Here's how it works. The scale runs from 0 to 10, with 0 meaning definitely natural, and 10 meaning definitely technological. Most objects sit at 0 or 1. Rocks, asteroids, comets, all the normal stuff we see in space rates is obviously natural, with no technological interpretation required. Moving up the scale requires evidence, specific criteria that shift probability away from natural explanations. The criteria include things like non-gravitational acceleration that can't be explained by outgassing or radiation pressure, geometric relationships that suggest navigation, compositional anomalies inconsistent with natural formation, apparent attitude control, correlation between multiple independent anomalies, and statistical implausibility of the overall behaviour pattern. 3i Atlas currently sits somewhere in the 3 to 5 range, depending on which analysis you're reading, and how conservatively you interpret the data. That's not confirmation. That's not even strong suspicion. But it's also not dismissal. It's acknowledgement that the object warrants serious consideration, that the technological hypothesis can't be ruled out based on current evidence, and that further observation is scientifically justified. The scale exists because binary thinking fails for edge cases. Either it's natural or it's artificial, is not a useful framework when dealing with ambiguous data. What you need is gradation, a way to say, this is unusual enough to pay attention to, but not unusual enough to make definitive claims. The Loeb scale provides that gradation, but more importantly, it provides legitimacy. For decades, suggesting that an astronomical object might be technological was career suicide. You didn't propose artificial origins unless you had overwhelming proof, and even then you'd be treated with suspicion. The stigma was so strong that most scientists wouldn't touch the topic, even when observations were genuinely anomalous. The Loeb scale changes that dynamic. It makes it acceptable to discuss technological possibilities as part of the normal scientific process of hypothesis testing and data interpretation. It destigmatizes the conversation. And that's why its quiet adoption represents a paradigm shift, even if most people haven't noticed yet. Think about historical parallels. Continental drift was stigmatized for decades. Alfred Wegener proposed it in 1912. The evidence was obvious. Continents fit together like puzzle pieces, similar fossils on both sides of the Atlantic. But geologists rejected it because they couldn't imagine a mechanism. They didn't have plate tectonics yet. so they dismissed the observations rather than accept a theory that seemed impossible. It took until the 1960s for plate tectonics to be accepted, 50 years of evidence accumulation before the paradigm shifted, and after it shifted everyone looked back and wondered how it wasn't obvious all along. The lobe scale is trying to prevent that kind of delay by giving scientists permission to explore technological hypotheses before the evidence becomes overwhelming. Meteorites had the same problem. Rocks falling from the sky were dismissed as folklore. Scientists in the 1700s confidently stated that stones could not fall from the heavens because there were no stones in the heavens to fall. When people reported witnessing meteorite falls, they were told they were mistaken, that they'd misidentified lightning strikes, or hallucinated, or were lying. It took decades and multiple witnessed falls before the scientific community accepted that yes, rocks do fall from space. The pattern is always the same. Observations that don't fit existing frameworks get dismissed, ridiculed, or ignored. The people proposing alternatives get marginalised. Then slowly, reluctantly, the evidence piles up until it can't be ignored anymore, and the paradigm shifts. And after the shift, everyone agrees that the evidence was obvious in retrospect. We might be in that pre-shift moment right now. The observations are there, the anomalies are documented, the statistical improbabilities are calculated. But the community isn't ready to accept the implications, because accepting them would require updating too many fundamental assumptions about what's out there and whether we're alone. The lobe scale gives us a language for talking about this uncertainty, without requiring premature commitment to either position. You can say, this rates a 4 on the lobe scale, and everyone knows what that means. It's unusual, worth investigating, not conclusive. It's a framework for scientific discussion that doesn't force binary choices, and it's being used now, quietly, in technical discussions and conference presentations and research proposals. The existence of the scale changes the conversation by making technological hypotheses a legitimate category of scientific inquiry rather than a fringe topic. But here's the thing about classification systems. They only matter if they lead to action. If 3i Atlas rates high enough on the lobe scale to warrant further study, what does that study look like? What observations would move it up or down the scale? What would constitute confirmation or refutation? Those are the questions driving planning for post-flyby analysis. And one of the most interesting hypotheses about what 3i Atlas might have been doing during its close approach is also one of the least discussed. Because if this is reconnaissance, you don't stop to say hello. You scan and you leave. And scanning makes more sense than any other mission profile. Part 10. Scanning, not visiting. Here's something most people misunderstand about flybys. They think of them as brief encounters, missed opportunities, moments where you almost made contact but passed each other by. That's the wrong frame. Flybys are optimal observation geometry. You get close enough for high-resolution measurements, but you're moving fast enough that you don't get captured, you don't have to spend energy on orbital insertion, and you preserve the option to continue to other targets. Every deep space probe humanity has sent has used flyby geometry when possible. Voyager's entire mission was a series of flybys. New Horizons flew past Pluto at 14 kilometers per second, close enough to image surface features but too fast to stop. That wasn't a limitation. That was the design. Flybys maximize data return per unit of mission complexity. If you're conducting reconnaissance of an inhabited system, flyby geometry has another advantage. You don't trigger proximity alarms. You don't establish orbit, which would be obvious and threatening. You just pass through, collect what you need, and continue outward. From the perspective of the local civilization, you're barely there. A blip on telescopes, a temporary curiosity, not a permanent presence. 3i Atlas's closest approach to Earth put it within about 140 million kilometers. That's close in astronomical terms, well within the range where high-resolution spectroscopy could characterize atmospheric composition, detect industrial signatures, map electromagnetic emissions across the spectrum. You don't need to be in low orbit to gather intelligence about a technological civilization. You just need to be close enough that your sensors have sufficient resolution. And what would you look for? Atmospheric composition tells you about biology and industry. Oxygen-nitrogen atmospheres with trace amounts of industrial pollutants scream technological civilization. Radio emissions tell you about communication infrastructure. Light pollution tells you about energy usage and population distribution. Infrared signatures tell you about heat dissipation, power generation. urban development. All of that is detectable from a distance. You don't need to land, you don't need to stop, you just need line of sight and enough time to point your instruments. And a close approach gives you both. Passive sensing is also strategically preferable to active sensing. Active sensing means you're emitting something, radar pulses, laser ranging, whatever. Active emissions can be detected, can reveal your presence, can mark you as a potential threat. Passive sensing means you're just watching, just collecting ambient light and radiation, not giving away your position. If you're trying to assess a civilization without alarming them, passive sensing during a flyby is exactly what you do. Now, here's where it gets interesting. 3i Atlas's closest approach happened to coincide with a moment when Earth, the Sun, and the object were aligned in specific geometry. That geometry matters for communication. If you're trying to transmit data back to a distant receiver, you want the Sun either behind you or in a position where it's not interfering with the signal. You want minimal background noise, clear line of sight to wherever home is. There's a debate, very speculative, very carefully framed, about whether 3i Atlas's perigee alignment might have provided optimal transmission geometry. If you drew a line from the object through Earth and out into space, where does it point? What's in that direction? Is there anything unusual about that vector? Some analysts have noted, and I want to emphasize this is not consensus, that the alignment bears some resemblance to the direction of the WOW signal. You remember the WOW signal, right? 1977, Big Ear Radio Telescope, 72-second burst of narrow-band radio emission from the direction of Sagittarius. Never repeated, never explained, never definitively classified as natural or artificial. Just WOW, written in the margin by the astronomer who noticed it, and then silence for almost 50 years. If 3i Atlas's transmission geometry pointed toward the WOW signal origin, that would be one more item in the probability stack. One more correlation that individually means nothing but collectively starts to suggest pattern. But let me be clear, this is highly speculative, based on rough calculations of perigee orientation and historical signal directions that we don't have precise coordinates for. It's not proof of anything. It's barely a hypothesis. It's just interesting. What's more concrete is that perigee geometry without interaction is itself notable. 3i Atlas came close, stayed sun-locked, presumably collected whatever data it was designed to collect if it's technological, and then continued outward. No attempt at communication from our side, no obvious transmission from its side, just mutual observation and departure. That's what reconnaissance looks like. You don't knock on the door, you don't announce yourself, you observe, you record, and you report back. And if you're reporting back to receivers light years away, you need clear transmission geometry, high-gain antennas or their equivalent, and enough time to send whatever compressed data package you've assembled. How long would that take? How much data could you realistically transmit across interstellar distances during a solar system flyby? We don't know. Our own deep space communication bandwidth is measured in bits per second at extreme ranges. Voyager is transmitting at 160 bits per second from the edge of the solar system, using 23 watts of power. Scaling that up to interstellar distances would require either enormous power, or very narrow beam widths, or incredibly long transmission times, or technology we don't have yet. But if you've travelled for millions of years to get here, you've probably solved the communication problem. And if you're sending reconnaissance data back home, you're not streaming video. You're sending compressed summaries, spectroscopic data, chemical signatures, electromagnetic profiles, high-value information in minimal bandwidth, the kind of thing you could transmit in a few hours or days with the right equipment, and then you continue to Jupiter, and maybe beyond. Because Earth might have been the high-priority target, but Jupiter is the strategic asset. Jupiter is where you leave infrastructure. Jupiter is where the mission might actually begin rather than end. But I'm getting ahead of the timeline. Right now, tonight, the focus is on Earth. The close approach is happening. Whatever scanning was planned is either complete or in progress. And tomorrow, we start analysing what we observed, what the object did, whether anything changed in the data during closest approach. And while we do that, the universe keeps reminding us that we don't understand it as well as we thought we did. Because 2025 has been a strange year for science, full of moments where our models broke and our predictions failed and our certainty evaporated. 3i Atlas is part of that larger pattern, and that pattern might be trying to tell us something. Part 11. AI discovers physics. We don't understand. Artificial intelligence solved protein folding. That's not hyperbole. That's fact. AlphaFold, developed by DeepMind, can predict protein structures with accuracy that rivals experimental methods, and it does it in hours instead of years. The AI doesn't understand biology. It doesn't know what a protein is. It just processes patterns in data and outputs predictions that turn out to be correct. That's wonderful and terrifying at the same time. Wonderful because it accelerates research, enables drug discovery, unlocks problems that were computationally intractable. Terrifying because we don't know how it works. The model is a black box. You feed it amino acid sequences, it performs millions of calculations through layers of neural networks, and it spits out a three-dimensional structure. But if you ask why that structure, what principle it's following, what understanding it has of the underlying chemistry, the answer is, we don't know. The AI has discovered something about physics that we can't articulate. It's found patterns in protein folding data that represent real physical principles, but those principles are encoded in weights and activation functions that humans can't parse. The tool works. The understanding is absent. This is happening across multiple domains. AI-designed materials that outperform anything human engineers created. AI-discovered chemical reactions that shortcut synthesis pathways. AI-generated solutions to fluid dynamics, problems that violate our intuition about how fluids should behave, but turn out to be correct when tested. In every case, the AI is right, and we don't fully understand why. That should concern you, not because AI is dangerous, but because it means intelligence can outpace intuition. We're creating systems that can solve problems we can't solve, using methods we can't follow, arriving at answers we can verify but can't derive ourselves. And if that's possible with human-created AI, what does it imply about intelligence that evolved elsewhere independently over different timescales? If an alien probe arrived in our solar system, would we recognize its technology? Would we understand its operating principles? Or would it look like magic, like something that works without comprehensible mechanism, like a black box that produces results without revealing method? Arthur C. Clarke said that any sufficiently advanced technology is indistinguishable from magic. That's true, but there's a corollary. Any sufficiently advanced technology might be indistinguishable from nature. If you don't understand the principles, if the engineering is beyond your intuition, you classify it as natural because that's the only category you have that fits. I don't understand how this works. We're experiencing this loss of explanatory comfort in our own technology. Neural networks function without full theoretical justification. Large language models generate coherent text through mechanisms we can only partially describe. Quantum computers solve certain problems exponentially faster than classical computers, but the physical interpretation of why is still debated. Intelligence is outpacing intuition, and that has implications for how we interpret observations of potentially technological objects in space. If we can't fully explain our own AI-generated discoveries, what hope do we have of recognizing alien engineering that might be millions of years ahead of us? The honest answer is, we wouldn't. Not immediately, not without extensive analysis. And maybe not at all if the technology is sufficiently advanced that our entire framework for understanding physics is incomplete. We'd see anomalies, we'd see patterns that don't fit, we'd see behaviours that violate our models, and we'd default to unknown natural process because the alternative requires admitting that something out there knows things we don't. This is why the lobe scale matters. It's a framework for moving past binary thinking, for acknowledging that I don't understand this is not the same as this must be natural. It's a tool for scientific humility in an era where our tools are smarter than our theories. And this is happening while other foundations are crumbling. Dark matter, the invisible scaffolding that's supposed to hold galaxies together, might not exist at all. Or it might exist in ways we didn't predict. Or we might need entirely new physics. The point is, we're not sure anymore, and that uncertainty cascades. Part 12. The quiet crisis in dark matter detection. Dark matter makes up 85% of the universe's matter, except maybe it doesn't. Or maybe it does, but not in the form we expected. Or maybe our understanding of gravity is wrong and dark matter is just a fudge factor covering up our incomplete theories. This is where physics is right now. Uncertain, uncomfortable, staring at decades of null results and wondering what went wrong. For 30 years, physicists have been building increasingly sensitive detectors to find dark matter particles. WIMPs, weakly interacting massive particles, the leading candidate for what dark matter might be made of. Build a detector deep underground, shield it from cosmic rays, wait for a dark matter particle to collide with a nucleus, detect the tiny energy release. Simple in principle, incredibly difficult in practice. And after 3 decades and billions of dollars in detector construction, the result is nothing. Not nothing. Null results. No WIMP detections above background noise, no signal that can't be explained by mundane sources, no confirmation of the particle physics models that predict what dark matter should be. Just silence where we expected discovery. That's not failure. That's worse. Failure means you tried something and it didn't work. Null results mean the universe isn't behaving the way your theory says it should. It means either your theory is wrong, or your assumptions about how to detect the thing your theory predicts are wrong, or the thing doesn't exist at all. Alternative theories are gaining traction. Modified Newtonian dynamics, MOND, which proposes that gravity behaves differently at galactic scales than it does in the solar system. No dark matter required, just a modification to gravity itself. That sounds radical, but it's been around since 1983, and recent observations keep giving it room to breathe. Galaxy rotation curves, gravitational lensing, large-scale structure, MIAND explains a lot of it without invoking invisible matter. Or maybe dark matter exists, but not as particles. Maybe it's primordial black holes, formed in the first fractions of a second after the Big Bang. Too small to detect individually, too numerous to ignore collectively. They'd have gravitational effects without electromagnetic interaction, which is what dark matter is supposed to do. But that requires specific formation conditions, specific mass distributions, specific probabilities that we're not sure the early universe could have produced. The point is, we're in a paradigm-adjacent moment. Not full paradigm shift yet, but close. The old model isn't working. Alternative models aren't conclusively better. We're in the uncomfortable zone where decades of certainty are evaporating and nothing solid has replaced them yet. This happens in science. Newtonian gravity worked perfectly until it didn't. Mercury's orbit precessed in ways Newton couldn't explain. For decades, physicists proposed ad hoc explanations. Extraplanets, modified gravitational laws, observational error. None of them worked. Then Einstein showed that spacetime itself is curved, gravity is geometry, and suddenly Mercury's orbit made perfect sense. The paradigm shifted. The old model became a special case of the new one, and everyone agreed that the evidence had been there all along. We might be in the pre-Einstein phase of dark matter. The anomalies are piling up. The observations don't match predictions. The community is starting to acknowledge that something fundamental might be wrong. But we don't have the new framework yet. We're still arguing about whether to modify gravity or particle physics or cosmology itself. We're in the chaos before the resolution. And this matters for 3i Atlas because it's a reminder that the universe surprises us. Constantly. Things we thought we understood turn out to be more complicated. Things we confidently predicted turn out not to exist. The map is always wrong in interesting ways, and humility is the appropriate response. If we can spend 30 years looking for dark matter in the wrong place, what else might we be missing? What other phenomena are we misclassifying because our models are incomplete? How many anomalies do we dismiss because they don't fit existing frameworks, even when the frameworks themselves are showing cracks? Fast radio bursts are another example. Bright, brief, energetic, mysterious. We've been detecting them for years now. We have thousands of them catalogued, and we still don't have a definitive explanation for what they are or how they're produced. They keep getting stranger instead of clearer. Part 13, Fast Radio Bursts. Get stranger, not clearer. Fast radio bursts are millisecond duration pulses of radio energy from cosmological distances. They're bright, brighter than entire galaxies for the fraction of a second they're active. They were discovered in 2007, and for the first few years, we only had a handful of detections. Now we've got thousands. And instead of clarifying the picture, the abundance of data is making everything more confusing. The early assumption was that FRBs were one-time cataclysmic events. Neutron star collisions, magnetar flares, something violent and singular that releases enormous energy in a brief burst. That model worked fine when FRBs were rare. Then we found repeating FRBs. Same source. Multiple bursts, sometimes periodic, sometimes random. One-time cataclysms don't repeat. So the models changed. Okay, maybe they're magnetar flares, which can repeat. Magnetars are neutron stars with absurdly strong magnetic fields, and they occasionally have crustal quakes that release energy that could produce repeating bursts, except the energetics don't quite match. FRBs are brighter than magnetar flares by orders of magnitude, and the periodicity some FRBs show doesn't match what we'd expect from neutron star rotation. Then localization improved. We started pinpointing which galaxies FRBs came from, and some of them are in galactic environments that shouldn't have magnetars. Young star-forming regions, sure, that's where you'd expect magnetars, but some FRBs are coming from old elliptical galaxies with no recent star formation, no young neutron stars, no obvious magnetar candidates. The more we learn, the less we understand. That's not supposed to happen. Data is supposed to narrow possibilities, converge on explanations, resolve mysteries, but FRBs keep violating expectations. They're too bright, too brief, too variable, too weirdly distributed across the sky and across cosmic history. Every new observation adds complexity instead of clarity. And here's the uncomfortable part. Some FRBs show patterns, not random noise, patterns. Periodicity and burst timing, frequency structure that looks organized, dispersion measures that suggest specific propagation environments. Pattern recognition in data like this is dangerous because humans are excellent at finding patterns in noise. But when multiple independent research groups using different analysis methods keep finding structure, you have to at least consider that the structure might be real. I'm not suggesting FRBs are artificial. That's an extraordinary claim that would require extraordinary evidence, and we don't have it. But the point is that we're confronted with a phenomenon that's been observed thousands of times, analysed by hundreds of researchers, and we still can't definitively explain it. We have models, but the models keep needing revision. We have candidates, but none of them fit all the observations. That's the current state of astrophysics, full of confident-sounding explanations that quietly fall apart when you look at the details. Full of phenomena that should be understood by now but aren't. Full of mysteries that familiarity has dulled into routine without actually resolving. We've normalised FRBs. They went from, holy shit, what is that, to, oh yeah, another FB in less than 20 years. We've filed them under interesting unexplained phenomenon, probably natural, and moved on. But what if we're moving on too quickly? What if the pattern overload is hiding something important because we've stopped being surprised? 3i Atlas sits in the same uncomfortable category. Lots of data, lots of analysis, lots of competing explanations, no consensus, and a creeping sense that maybe the reason we can't explain it is because we're looking at it through the wrong frame. But before we get lost in distant galaxies and cosmological mysteries, let's look closer to home. Because the solar system itself, our immediate neighbourhood, is turning out to be less settled than we thought. Part 14. Solar system anomalies closer to home. Mars is losing its atmosphere faster than models predicted. Not catastrophically, not crisis level, just consistently faster than the equations say it should. That's been known for years, confirmed by multiple missions, Malvern orbiter data, decades of atmospheric measurements, and we still don't have a complete explanation. Solar wind stripping accounts for some of it. The charged particles from the sun slam into the upper atmosphere, ionize molecules, and carry them off into space. We understand that mechanism, we've measured it. But the numbers don't add up. The rate of loss is higher than solar wind stripping alone can explain. Something else is happening, some process we're either underestimating or missing entirely. You might think that's not a big deal. Mars is a dead world, right? What does it matter if we're off by a percentage point or two in atmospheric loss calculations? It matters because if we can't accurately model atmospheric escape on a planet we've been studying intensively for 50 years, what else are we getting wrong? What other slow processes are operating in ways our equations don't capture? The Mars anomaly is small, but it's persistent, reproducible, and unexplained. That's the signature of incomplete physics. Earth's magnetic field is weakening in the South Atlantic. The South Atlantic anomaly, they call it. A region stretching from South America across to southern Africa, where the field strength has dropped significantly over the past century. Satellites passing through this region experience higher radiation doses. Astronauts on the International Space Station get measurably more cosmic ray exposure when they orbit through it. Electronics malfunction more frequently. It's a real effect with real consequences, and while we know the field fluctuates naturally, the rate of change in this particular region is faster than models predicted. The Earth's magnetic field is generated by convection in the liquid iron outer core. That's the theory. The geodynamo, swirling molten metal creating electric currents that produce magnetic fields. We've got the basic picture, but the details are messy. The field wanders, the poles drift. Sometimes the whole thing flips. North becomes south, south becomes north. We know this happens because we can read the magnetic signature frozen into ancient rocks. Polarity reversals occur every few 100,000 years on average. Except we're overdue for one. The last reversal was 780,000 years ago. And the South Atlantic anomaly might be the early warning sign of the next flip. Or it might not. We don't know if it's the start of a magnetic pole reversal or just normal variation amplified by something we don't understand. We're watching and measuring, but not really understanding. The models can't predict whether this continues, accelerates, or reverses. We're in reactive mode, documenting what happens without being able to forecast what comes next. That's not a comfortable position for a civilization that depends on satellites and power grids and electronics that all assume a certain amount of magnetic shielding from cosmic radiation. Jupiter's atmosphere is doing things we didn't expect. Storm systems that should dissipate persist for decades. The Great Red Spot has been raging for at least 300 years, possibly longer. That's impossible according to terrestrial atmospheric dynamics. Storms on Earth last days, maybe weeks for the largest hurricanes. They dissipate when they run out of energy or encounter land or lose their organisational structure. Jupiter has no land, but its storms should still lose coherence over time. Turbulence should break them apart. Energy should radiate away. But the Great Red Spot keeps spinning, and while it's been shrinking slowly, it's still there, still organised, still violating our intuition about how long-lived atmospheric structures can persist. Energy outputs that should match solar input don't. Jupiter radiates more heat than it receives from the Sun. That's been known since the 1970s. The planet is still contracting from its formation, releasing gravitational potential energy as heat. That explains some of the excess, but the numbers are borderline. The amount of internal heat, the rate of radiation, the persistence of the signal, all of it suggests processes that we understand individually but struggle to model collectively. And Juno mission, data keeps finding surprises. Ammonia distribution that doesn't match predictions. Atmospheric circulation patterns that extend deeper than models suggested. Magnetic field complexity that implies internal structure we didn't anticipate. Auroral emissions that should correlate with solar activity sometimes don't. Jupiter has the brightest auroras in the solar system, powered by its enormous magnetic field and volcanic moon, Io, continuously pumping charged particles into the magnetosphere. Most of the time, the auroras behave predictably, but sometimes they flare independently of solar wind conditions. Sometimes they pulse in ways that suggest internal magnetospheric dynamics we don't fully understand. It's not alarming, it's not crisis level. It's just consistently surprising in small ways that accumulate into a general pattern of, we thought we understood this better than we do. Saturn's rings are younger than we thought. Way younger. Like maybe only a few 100 million years old, not billions. Cassini mission data from its final plunge through the ring system gave us precise mass measurements, and those measurements tell us the rings are mostly clean ice, very little dust contamination, and dust accumulates over time from micrometeorite bombardment. If the rings were ancient, billions of years old like Saturn itself, they'd be darkened by dust. But they're bright, clean, young. That's weird because it means Saturn spent most of its existence ringless and only recently acquired its most distinctive feature. How? We don't know. Comet impact that shattered an icy body near Saturn? That could produce ring material. Moon disintegration. Tidal forces tearing apart a satellite that wandered too close? That's possible. Capture of a passing object that got ripped apart? Maybe. Something we haven't thought of yet? Probably. Pick your hypothesis, none of them are fully satisfying. All of them require specific initial conditions, specific timing, specific circumstances that seem unlikely but must have happened because the rings exist and they're young. The universe apparently doesn't care about our sense of likelihood. Pluto's surface is geologically active. We saw that when New Horizons flew by in 2015. Active ice glaciers, fresh resurfacing, evidence of cryovolcanism. Sputnik Planitia, the heart-shaped plane, shows convection cells in nitrogen ice. The surface is young, maybe less than 10 million years old in some regions. There are no impact craters where there should be impact craters. That means something is resurfacing the area, erasing the scars of bombardment, maintaining geological youth on a body that small, that far from the sun, that should have been geologically dead billions of years ago. Internal heat sources, radiogenic decay of uranium, thorium, potassium in the core. That's the standard explanation. But Pluto is tiny, only 2,370 kilometres across. Small bodies cool quickly. They don't retain enough heat to drive geological activity over 4.5 billion years. You need additional energy, tidal heating from Charon. Pluto and its moon are tidally locked to each other, so ongoing tidal flexing should be minimal. Historic tidal heating when the system was first forming? Maybe, but that energy should have dissipated long ago. Again, we have proposals, but the energetics are borderline. Pluto is more active than it has any right to be, and every explanation requires pushing the boundaries of what we think small, icy bodies can do. Enceladus is spraying water into space. Saturn's moon, tiny ice ball barely 500 kilometres across, geysers erupting from the South Pole, subsurface ocean, potential habitability. None of that was predicted. We thought Enceladus would be geologically dead like most small moons, cratered, frozen, boring. Instead, Cassini flew through plumes of water vapour and ice crystals being ejected at hundreds of kilometres per hour. We discovered it by accident when the spacecraft detected unexpected particles in its instruments. Subsequent observations confirmed an entire system of geysers, fractures in the ice nicknamed tiger stripes, a liquid water ocean underneath heated by tidal flexing from Saturn's gravity. But the amount of heat required, the persistence of the activity, the chemistry of the plumes, all of it pushes the boundaries of our models. Enceladus shouldn't have enough tidal heating to maintain a subsurface ocean. It's in an orbital resonance with Dione, another of Saturn's moons, and that resonance amplifies tidal forces. But even accounting for resonance, the energy budget is tight. The moon is generating more heat than our calculations comfortably explain, and the plume chemistry shows organic molecules, salts, silica nanoparticles suggesting hydrothermal activity at the ocean floor. That's Earth-like chemistry on a moon 1/7 Earth's diameter. That's a complete ecosystem worth of complexity that we never anticipated. Everywhere we look closely, we find surprises. Not dramatic, not paradigm-shattering individually, just persistent deviations from expectation. "We didn't predict this" is becoming a common refrain in planetary science. And while each anomaly has proposed explanations, none of the explanations are slam dunks. They're plausible, they're possible, but they're not certain. They require invoking special circumstances, boundary conditions, processes operating at the edge of what we think is possible. One surprise is interesting. 10 surprises across different bodies in different environments starts to suggest that our models are systematically underestimating complexity. This is the epistemological state of the field. We're less sure than we used to be. We're more comfortable with uncertainty, and that's probably healthy. Overconfidence breeds blind spots. Humility breeds curiosity. But it also means that when something like 3i Atlas shows up with its stack of anomalies, we're less equipped to confidently declare this is definitely natural, because we've been wrong about that too many times lately. Every planet we've studied up close has surprised us. Every moon with active geology has challenged our preconceptions. Every atmospheric measurement has revealed dynamics we didn't anticipate. So why would we assume perfect understanding of an object that might not even be from our solar system? The solar system is teaching us that complexity persists even close to home, that familiarity doesn't equal understanding, that local doesn't mean simple. We've sent spacecraft to every planet. We've mapped surfaces, measured compositions, sampled atmospheres, and every mission reveals new puzzles. Some puzzles get solved, others just get documented and filed under interesting needs more study. The archive of unsolved solar system mysteries is embarrassingly large for a civilization that considers itself scientifically sophisticated. And if we're still figuring out basic things about our own planetary neighbours, what hope do we have of correctly interpreting an object that might have come from light years away? If Mars' atmospheric loss is still unexplained after decades of study, how confident should we be about our explanations for 3i Atlas's outgassing? If Pluto can be geologically active against all expectation, why couldn't a comet-like object maintain attitude control through mechanisms we haven't imagined? The track record doesn't inspire confidence in our ability to rule things out definitively. Observer bias is a thing. We see what we expect to see. We interpret data through frameworks built from prior experience. And when the data doesn't fit the frameworks, we either expand the frameworks or dismiss the data as outliers. Rarely do we stop and ask whether the frameworks themselves might be incomplete. That requires intellectual humility bordering on painful. It requires admitting that decades of work might be based on assumptions that seemed reasonable at the time but turn out to be wrong. Scientists are human. Humans resist paradigm shifts. It's easier to add epicycles to tweak parameters, to invoke special cases than to admit the whole model needs rebuilding. 3i Atlas challenges frameworks. It sits in the gap between definitely comet and definitely something else. And instead of resolving into one category or the other, it seems to be expanding the gap, making the boundary between natural and artificial less clear, more permeable, more uncertain. Maybe that's because the boundary was always blurry and we just pretended it was sharp. Maybe nature and technology aren't as distinct as we'd like to think. Maybe the universe produces things that don't fit our categories, and our insistence on categorization is the problem, not the objects themselves. And maybe that's the real Black Swan event, not the object itself, but us noticing, us asking questions we haven't asked before, us acknowledging possibilities we've dismissed too quickly. The event might not be out there in space. It might be in here, in the shift of perspective, in the moment we realize that certainty is overrated and curiosity is undervalued. The moment we stopped being confident about what we know and started being honest about what we don't. That's the shift. That's the threshold. And tonight, as 3i Atlas makes its closest approach, we might be crossing it without even realizing until we look back from the other side. Part 15. The Real Black Swan. History is terrible at recognizing turning points as they happen. We label them afterward, once we know how the story ends. This was the moment everything changed. But people living through the moment don't know that. They're just dealing with whatever's happening right now, making sense of it with the tools available, trying to decide if it's important or not. The present moment is always too close, too immediate, too cluttered with noise to see clearly. We lack the perspective that distance provides. We can't know which details matter and which are just background static until the pattern completes itself and we can trace the line from cause to effect. September 11th happened, and people knew immediately it was significant. The towers fell on live television. The Pentagon burned. A field in Pennsylvania became a crash site. The visceral impact was undeniable. But the full implications, the wars in Afghanistan and Iraq, the surveillance state, the Patriot Act, the transformation of air travel from routine to ordeal, the erosion of privacy, the normalization of security theatre, all of that unfolded over years. The event was obvious. The consequences took time to manifest. And some consequences are still unfolding 20+ years later. We're still living inside the ripples of that day, still discovering ways it changed us that weren't apparent when it happened. The invention of the printing press in 1440 was transformative, but Johannes Gutenberg didn't know he was starting the Reformation, the scientific revolution, the Enlightenment. He was just trying to print books more efficiently. He wanted to make Bibles faster and cheaper. That was the immediate goal, a business proposition, a technical challenge. The printing press enabled those transformations, but they weren't visible at the moment of invention. They emerged slowly over generations as the technology diffused and its implications played out. Martin Luther's 95 Theses wouldn't have mattered without printing presses to distribute them. Copernicus and Galileo couldn't have challenged the Church without printed books spreading their ideas. The Enlightenment required widespread literacy, which required cheap books, which required mechanical printing. But Gutenberg couldn't see any of that. He saw type and ink and economics. Black swans are like that. The event itself might be visible. The significance might not be. You might know something happened without knowing what it means. And the gap between happening and meaning can be days, years, centuries. The fall of Constantinople in 1453 seemed like a military defeat at the time. Only later did historians recognize it as the event that pushed Greek scholars westward, carrying manuscripts and knowledge that helped trigger the Renaissance. The event was one thing. The meaning was something else entirely, something that only became clear when viewed from a distance. 3i Atlas might be that kind of event. Something happened. An object with unusual properties passed through the inner solar system. We observed it. We documented it. We collected spectra, measured trajectories, calculated accelerations, noted anomalies. We argued about what it means, we published papers, we had conferences, we built models, and we might not know the answer for a long time. Maybe never. Maybe it's one of those things where future historians will look back and say, that's when we should have known, but we didn't because we were too close to see clearly. Because we were blinded by our own assumptions about what was possible and what wasn't. Or maybe it's nothing. Maybe all the anomalies resolve into natural explanations given enough time and better data. Maybe in 5 years, we'll have a complete understanding of 3I Atlas's composition, origin, and behaviour, and it'll fit comfortably into the category of interesting comet, taught us new things about cometary dynamics, no technological hypothesis required. Maybe we'll discover a new outgassing mechanism, a new type of ice structure, a new way that gravitational interactions can produce coherent behaviours. Maybe the anomalies will turn out to be artefacts of measurement error, or observational bias, or incomplete models that get corrected with better instruments and longer observation windows. Both outcomes are possible. Uncertainty is honest. What's dishonest is pretending we know more than we do. What's dishonest is dismissing possibilities because they're uncomfortable, or accepting them because they're exciting. The data is ambiguous. The interpretations are contested. Different research groups looking at the same observations reach different conclusions, and that's not a failure of science. That's science working exactly as it should. Multiple hypotheses competing, evidence accumulating, consensus forming slowly through replication and scrutiny, and that's okay. That's how science works when it's working properly. The discomfort comes from wanting certainty before we've earned it. But here's what matters. Questions matter more than answers right now. The question, could this be technological, is on the table. That question is scientifically legitimate because there's evidence supporting it. Evidence that hasn't been explained away. Evidence that fits patterns we'd expect from artificial objects. The 16-degree deflection, matching twice the jet opening angle, the sustained sunlock orientation, the compositional anomalies, the trajectory toward Jupiter. Each piece might be explicable individually, but the stack is harder to dismiss. Asking the question doesn't require believing the answer is yes. It just requires intellectual honesty about what we're observing. It requires acknowledging that natural isn't the only category available, and that ruling out artificial explanations should require positive evidence, not just absence of proof. Cultural readiness matters. If a society isn't ready to hear an answer, the answer won't penetrate, even if it's correct. Pre-Copernican Europe wasn't ready to hear that Earth wasn't the centre of the universe. The evidence was there: retrograde motion of planets, the phases of Venus, the moons of Jupiter. Galileo saw them through his telescope and understood what they meant. The math worked. Aristarchus had proposed heliocentrism 1800 years earlier based purely on geometry. But the cultural framework couldn't accommodate it without upheaval. It challenged religious doctrine, philosophical assumptions, humanity's sense of its own importance. Eventually the framework changed, but it took time. It took generational turnover. It took people being born into a world where the new idea was normal rather than threatening. It took deaths, both literal and professional, of people who couldn't or wouldn't accept the evidence. We might be in a similar transition now. A generation that grew up with SETI, with exoplanet discoveries numbering in the thousands, with the understanding that the universe is vast and full of potential homes for life. That generation is more ready to consider technological explanations than previous generations were. They grew up watching science fiction become science fact. They saw private companies launch rockets, saw rovers drive on Mars, saw gravitational waves detected, saw black holes photographed. The impossible became routine. And that changes what seems plausible. The stigma around discussing alien technology is fading. Not gone, but fading. And that creates space for ideas that would have been career-ending 30 years ago to become legitimate research topics. The Loeb scale exists now. That's progress. That's permission structure. That's the scientific community acknowledging that the question is worth asking, even if we don't have the answer yet. Scientific courage matters. It takes courage to propose hypotheses that your peers might ridicule. It takes courage to publish papers that challenge consensus. It takes courage to say, I don't think the standard explanation works, when everyone else is nodding along. Loeb has that courage. Whether he's right or wrong about 3I Atlas, he's asking questions that need asking. and he's doing it publicly, transparently, with data and reasoning. That's valuable regardless of outcome. Even if 3i Atlas turns out to be entirely natural, Loeb's willingness to explore technological hypotheses pushes the field forward. It forces other researchers to be more rigorous in their natural explanations. It makes dismissal harder because now there's a competing framework that has to be explicitly ruled out rather than ignored by default. And here's the thing about tonight. Nothing has to happen for this to be historic. No explosions, no contact, no revelation, no alien transmission, no sudden course change, no dramatic display. The flyby might be completely unremarkable from a spectacle perspective. 3i Atlas passes, continues outward, leaves us with data to analyse. That's it. The telescopes track it, the spectrometers measure it, the orbit calculators update their models, and then it's gone, receding into the outer solar system, heading toward Jupiter, eventually toward interstellar space again. From a drama perspective, it's boring. Nothing happened. But the perspective shift matters. The moment we stopped being able to comfortably dismiss this as just a comet and started having serious conversations about what if it's not, that's the shift. That's the event, not the object. The conversation about the object, the fact that mainstream astronomers are using frameworks like the Loeb scale, the fact that technological hypotheses are being published in peer-reviewed journals, the fact that we're collectively acknowledging that the question is legitimate even if the answer remains uncertain. That's the paradigm shift happening in real time. Not a conclusion, a process, a gradual erosion of the old certainties and a cautious exploration of new possibilities. Recognition matters more than confirmation. If 3i Atlas forces us to develop better methods for distinguishing natural from artificial objects, that's progress, even if this particular object turns out to be natural. If it forces us to acknowledge gaps in our understanding of cometary dynamics, of orbital mechanics, of ice physics, of outgassing behaviour, that's progress. If it makes us more careful about dismissing anomalies, more humble about our models, more willing to consider alternatives, that's progress. The object itself might be less important than what studying it teaches us about how we study things, about our biases, about our assumptions, about the gaps between what we think we know and what the data actually tells us. The paradigm doesn't shift when the evidence arrives. It shifts when the community is ready to interpret the evidence differently. And maybe tonight, maybe this flyby, maybe this conversation, maybe this is the moment readiness catches up with evidence. Or maybe it's not. Maybe we need more time, more data, more anomalies, more examples. Maybe 3i Atlas is the first hint of something that won't become clear until we see the second and third and 10th similar object. Maybe it's the opening note of a pattern that takes decades to recognise. Or maybe it's unique, singular, never to be repeated, and we'll spend the rest of our lives wondering what we saw and what it meant. But we're closer than we've ever been to asking the right questions without apology. And that matters. That's movement. That's evolution of thought. That's the scientific process functioning the way it's supposed to, slowly, painfully, grudgingly, admitting that the universe is stranger than we thought, and we need to expand our categories. Every generation of scientists believes they've figured out the basics and they're just filling in details, and every generation gets surprised. Quantum mechanics surprised classical physicists, relativity surprised Newtonians, dark energy surprised cosmologists, and whatever comes next will surprise us because that's what the universe does. It refuses to be fully known. It always has another layer of strangeness waiting underneath. So what happens tomorrow? We analyse the data, we compare predictions to observations, we see if 3i Atlas did anything unexpected during closest approach. We track its trajectory toward Jupiter, we publish papers, we argue in conference rooms and on preprint servers and in the peer review process. We propose new observations, we wait for better instruments, better models, better theories, and we stay uncertain because certainty is the enemy of curiosity. Certainty closes doors, uncertainty keeps them open, and right now we need open doors more than we need comfortable answers. And maybe in a year or 5 or 10 we'll look back at tonight as the moment when everything changed. The night when humanity stopped being alone in the universe, even if we didn't know it yet. The night when evidence of technological intelligence passed through our solar system and we were just barely sophisticated enough to notice. Or we'll look back and laugh at how worked up we got over a comet. How we saw patterns in noise and convinced ourselves something extraordinary was happening when really, It was just another rock tumbling through space. Either way, we'll have learned something. Either way, the conversation mattered. Either way, we took the question seriously enough to investigate rather than dismissing it out of hand. Nothing happened tonight, except awareness, except questions, except the possibility that we're not alone, and that the evidence of that fact has been passing through our solar system while we argued about whether to take it seriously, except the recognition that uncertainty isn't weakness, it's honesty, except the realization that the universe doesn't care about our comfort levels and will show us things we're not ready to interpret and force us to grow or remain ignorant, except the moment when we collectively decided that asking what if was more important than protecting our assumptions. The Black Swan is never the event, it's the realization, and the realization might already have happened. We're just waiting to see if we believe it.